Okay, ready? All right. So what I was mentioning was, you find a medium in which you can put your molecule and then confine its freedom that would lead to some selectivity in chemical reactions, or you have some control on the molecule by using these external surroundings. So the various types of structures are like these here, but if you look at all of them, at the end they are all very similar, although each one looks slightly different. The way it has is, they all have a big empty space. This empty space is fixed. It is like, it can be very small. It can be 5 angstroms, 10 angstroms, or 25 angstroms. So it is a smaller or bigger or bigger. So what happens is, you put your this kind of structures are called as supramolecular containers. Everything is a container. This is a container. This is a container for holding my water, and this one is a container holding more water and things like that. But this one is a container, but this container is tiny. It is extremely small, you cannot even see it. Okay? So we are going to put the molecule inside here. This is the molecule that we are interested in, and if you activate this molecule cannot escape. So like this water that is inside this container, it doesn't escape, it stays inside. So similarly, if you put this molecule inside this container, it is going to be stuck inside. Okay? And then now you activate this, it does something. Sometimes what happens is that it may do a chemical reactions. Chemical reaction is basically the atoms in a molecule, they rearrange. When they rearrange, they become either bigger or it becomes smaller. If it becomes bigger, then it is not going to happen, because this container is small, so the reaction is going to be more selective. So this is what is called as empty space. So inside a container, you can hold the molecule very tight. So for example, if you put this molecule is going to be moving around inside this space, so it has got some freedom. If you don't want that freedom, you need to put the molecule, clamp the molecule inside. Like you can have some various structures which can push the molecule, for example, hold the molecule inside, and these things are weak interactions. These are not covalent bonds. Covalent bond means you have to synthesize, you have to do a lot of synthesis. So these are some weak interactions that is holding this molecule inside the container. Okay, it is like if you have a lion, and a lion is pretty scary, you put them in a cage, and then it is still wandering around the cage, but you don't like this lion wandering around. You put some string on its neck and then tie it to the wall, then it will not move around, it will be stuck inside. But if you really make this string made out of iron or something, then you cannot cut it. If it is weaker, when you need, you just take it out, and then it can go outside and all this. So these are weak interactions. There are various types of weak interactions. Covalent bond is something like a carbon-carbon bond. Carbon, there are 2 electrons which are holding this carbon and carbon, and it is not easy to break. So you have to do some reactions to break the bond. But if you have carbon, there is one molecule here, another molecule here. If these two are not strongly held, that means you can remove this thing whenever you need. You can take it out. So the force that is holding these two must be very weak, like 2 kilocalories, 5 kilocalories, like that, so that when you pull it, it comes apart. So those are the kind of the forces that will be holding this molecule inside a supramolecular structure. Okay, for example, have you heard of any of these things? Cation pi, pi, hydrogen bonds, CH pi, van der Waals, charge transfer. Any of these things you have heard? You have heard. Which ones you have heard? All of them? All of them. Okay? All right. So, she has read all of them. Okay. Some of you might have read, or some of you may not have read. So, but these forces are only about 5 kilocalories. A chemical bond is about 100 kilocalories. 100 kilocalories is like a strong cement. So, it is not easy to break. On the other hand, 5 kilocalories is like a small glue, and then you stick it, and then when you need, you just pull it apart, it will come apart. Okay. So, the weak interactions, I will tell you a few of them, although she thinks she knows many of them. So, these are the various types of structures. Okay. So, I told you at the very beginning, Pedersen, who discovered this crown ether. So, how does the sodium or potassium or any kind of metal ions stay inside this? See, this is the structure, and then if you drop a sodium here, why would it stay inside? They can always come back to water or sodium plus, because sodium plus is more soluble in water and all this stuff. So, the force that is holding this metal ion, for example, the M plus, it could be a sodium plus or potassium plus or CCM plus or whatever. So, that one is interacting with in water, they will be solvated. That is why it is soluble in water. Sodium chloride is water soluble. Why it is water soluble? Because sodium plus, it forms interact with the water molecules. So, then sodium disappears into the water, and other Cl minus also disappears in water. So, it is, we call them as it is dissolved. It is dissolved in water. But sodium plus, this one is not water. This is an organic compound. Inside the organic compound, why does it go? That is because of these ion dipole interactions. These interactions are weak. It is about 10 kilocalories or things. What happens is, if you have a sodium plus here, and all the oxygens, if you remember, we kept saying before, oxygen has got a lone pair. We already said, okay, there are 2, 4, then you need 8 electrons, so there is 2 here, lone pair. So, the lone pair of oxygen can interact with the metal which is positively charged, because a lone pair means it is negatively charged. So, it gets attracted to the positively charged cation. So, as you see here, this is a metal ion potassium. Okay. So, it interacts with the lone pair, interacts with the lone pair, lone pair, lone pair. So, it stays in the middle. Okay. So, now this is an organic compound, and then outside organic, it does not know the sodium. So, now the whole thing will dissolve. So, sodium potassium permanganate, potassium plus, which is not soluble in hexane, it will get dissolved in hexane. It is because of this kind of binding between potassium plus and this compound. Same, so if you notice, they all contains oxygens, or it contains nitrogen because you need this lone pair. Okay, this is what is called as ion dipole interactions. So, each one has a different name. Okay. Because without these interactions, this potassium plus will not stay. Suppose you have only a CH2, 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 then this potassium is not going to stay inside. These oxygens are very critical. So, sometimes, anything with a lone pair is better. So, for example, you see here the nitrogen, these types of compounds were first made by Pedersen when he was working for DuPont company. Okay. He has no PhD, he has only masters. So, you usually think when somebody gets a Nobel Prize, this guy must be falling from heaven. No. So, this is a ordinary person, and he has only got masters, and he was born in Korea, somewhere close to this area, close to this country, and then eventually settled in America. And this one, for example, it is called as dipole interactions. This is not, again, these are all not covalent bonds or ionic bonds. Covalent bond or ionic bonds are very strong, and we need a weak bonds, but then so that it can be removed when it is needed. For example, in the last structure, if you have the potassium inside this, If you put it in water, potassium will come out. So you need something where it can easily go in and out. If you take it into the hexane or benzene, it will stay here. So depending on the medium, it can. Okay. So do you know what is a dipole interactions? Dipole. Suppose there is a sodium plus and Cl minus. Is there an attraction between them or they repel each other? Sodium plus and Cl minus. Do they attract or they push each other away? Okay. So plus and minus will always attract. Okay, like a boy and a girl, in principle they attract each other. Okay, so similarly, sodium plus has a permanent charge, Cl minus has a permanent charge. So when they come close, they come together. And then when you put in water, sodium plus solvated by water, Cl minus, so they separate. Okay, so this compound is the ketone. It doesn't have a charge, or HCl, it doesn't have a charge. Okay, but still they attract each other. Okay, so for example, the carbonyl is this compound. This is this here. Okay, HCl. Okay, and then or you have this compound, right? These compounds are not like sodium chloride. Sodium chloride actually is sodium plus Cl minus. But here the attraction is ionic attractions. The plus and minus, they attract each other. HCl and the carbonyl, these are two independent compounds. HCl will attract another HCl. Carbonyl will attract another carbonyl. Okay, that attraction is coming from what is called as dipole. Okay, dipole is basically these molecules have a dipole moment. The chlorine is going to draw the electron towards this. In the carbonyl, oxygen is going to draw electron towards it. So what will happen is this one is going to be delta minus and delta plus and minus. So it doesn't have a permanent charge, but then this is minus. So it is going to attract this end close to that. So the acetone, for example, they attract each other like this here, minus and plus, and this minus will attract this plus will attract this minus, so they stay together. Okay, but this attraction is not very strong, so you can just it will fall apart. Okay, so these are the kind of attractions that are used to hold the molecules inside these big supramolecular structures. Okay, there is another one called as cation phi. Like if you take a benzene and add sodium chloride will stick to the benzene because the benzene is electron rich, and then so it's something which is plus, it can get attracted but not very strong, but there is a weak interaction between them, and that is about 1 to 20 kilocalories. That is not a lot. Okay, the chemical bonds are 100 kilocalories and above. Okay, so okay, this is the most important. Okay, have you seen, in China there are a lot of lotus flowers. Okay, I have seen in Beijing, there are millions of these lotus flowers in various ponds. In America, if I see one lotus pond in 1 year, it's a big deal. There is no, we don't have a lotus in that, is not common. Here, it is so common, but I don't know whether you have noticed. If you look at the lotus leaves, the water will not stick to the lotus leaves. See, for example, this is a picture of a leaf, and this is the water. Next time when you go to the lake, you look at the leaves. If you drop water on the leaf, it will not stick. It will form a ball. It will form immediately. Turn around, it will look like a small ball. Because, or if you drop the water on some other leaf, like some parsley or something that you eat, put the water, it will spread. It will not form a ball, because this water and this leaf, they repel each other. So when they repel each other, they want to maintain only a very small contact with each other. So this is called hydrophobic. So This is because this leaf is made up of organic layer and water is not organic. So, organic and the water, they do not want to see each other. So, whereas the other leaves are, they contain some other organic materials and water, water a little bit. So, they attract. So, they will spread. Okay. And this is called super hydrophobic. That is because of this, what happens is, if you have an organic molecule in water, they will push the organic molecule away from water. Okay. So, now the organic molecule is if I drop an oil inside this water, the oil is not happy. It would have been happier in the bottle, but now I dropped it here. It is so unhappy. It is going to find a place to run away from water. Okay. So, that particular effect is called as hydrophobic effect. So, for example, you take here, this is a long hydrocarbon chain, CH2, 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 lot of CH2s. It is totally organic. It cannot stand water, because the water that is outside, as you see here, they are all hydrogen bonded to each other. This is an organic compound. In water, the water molecules are surrounding this molecule and making it very uncomfortable, because all these water molecules are holding each other and then trying to push this compound out. But now in the process, what happens is, this one normally they would have formed various types of hydrogen bonds among themselves. Because of this molecule, they are not able to interact. This oxygen and that oxygen is not able to form a hydrogen bond. So, they want to get together. So, they will slowly push this to this, and eventually it ends up like this. Okay. So, this is it is called hydrophobic effect. So, if you put an organic molecule in water, there is a repulsion between the organic and the water molecules, and because of this, the organic always wants to look for another organic molecule with which it can be close. So, for example, you have proteins. The body is filled with water. Everybody is, we are like water bottles. We are the water bottles carrying a lot of water around, and then inside this water we have a lot of organic molecules, enzymes. There are various enzymes which do a lot of chemistry, but when you take a food, it is all organic. That goes, it is not water soluble, but then these enzymes which are organic, they will take it away. As soon as you eat something, these enzymes will pick it up, because it has to go through water, but the compound that you eat, it does not want to be in water. So, it goes into the enzyme and then it undergoes a whole bunch of reactions. So, this is the principle of using the organic molecules in water. For example, all the compounds I showed you at the very first slide, cyclodextrins, micelles, all of these things are water soluble, but inside the water soluble there is a small hole. So, if you have an organic molecule, it will go inside and stay inside the hole. So, it does not want to even know where it is. Okay. So, these structures are called as host, or they are called as supramolecular structures. It can be an enzyme or a protein, or it can be simple micelles, cyclodextrins, or any one of these things. Simply all of them under the name of a host. And the host, this is called as a guest. That is the molecule that you are interested in is called as guest. The guest is not water soluble. The host is water soluble. If you put them together in water, the guest will go inside this. So, this is a host, the guest host complex. Complex means they want to be together, but they are not very stable. It is just like a guest at, when somebody comes to your house, for the 1 or 2 days is okay. You are happy the guy is there. That is, but then if he stays for 1 month, everybody is unhappy in the house. So, so this guest molecule will stay in the host for a short time, but it cannot be there forever. If it is there forever, that would be a chemical reactions. So, now this is what we use. This is the guest, you put it inside the host, and this guest can be, you can use the light to activate the guest, and when it does activate, it has to do everything inside this small area. and that is what we will talk about. Okay. I think we will. Okay, so for example, you take here this is a guest, which is a reactant, and when you excite the molecule, it can give you one product which looks like this, or it can give you another product looking like this. So when you have some molecule, it is excited, and then it is going to go to your product, which gets bigger, or it goes something which gets smaller. Okay. If you do this reaction in organic solvents in a beaker, both would be formed. Where this molecule gets bigger or it gets smaller, in a regular beaker, there is no problem. Both would be formed. Whereas if you do this reaction inside a container which is small, and if it wants to get this one or this one of them is going to be formed. Okay, so it gets bigger or it gets smaller. Tell me which one would be formed inside a small container. Suppose I put the molecule in this bottle, or I put the molecule inside a big bucket. Okay, so inside this, when there are two possibilities going here and going there, which of these two you think would be formed inside this container? Container is a host. Which one? Huh? Which one? Okay, so this is the one which is going to be formed. But if you take this thing without this ring around this thing, both would be formed, because there is no problem for this, because if it gets bigger, it has no space around it, so it cannot just expand, so it will just go smaller. So that is one way to make this reaction highly selective. So if this molecule reacts to give you two products in the solvent, you can make it to give you only one. Okay. Okay. So these are for example, here take this molecule. There are some weak interactions. These are supposed to represent like a dipole-dipole hydrogen bond like this. So this is our molecule, and it is interacting with the walls of the capsule, walls of the container. Now when it does react, what can happen is some of these things can peel apart. So when it is changing into two products like this one or that one, this one or that one, if you notice, when it goes from here to here, all these weak interactions are coming apart, whereas here it is still maintaining every one of those things. So when you have two possibilities, the reaction will proceed this way but not the other way. Whereas in a normal solution, this is not the problem, because normal solution, this molecule is not interacting with anything, so it is alone. Whether it goes here, whether it goes here, it does not make any difference. Whereas when it goes inside the capsule, then it is going to be different. So that is the idea of this. Okay, now, okay, we will just go something else. I just want to talk about some photophysics. Okay. Okay, you cannot even see this stuff. Okay. Now we talked about fluorescence, phosphorescence, various types of emissions and all this stuff, but they all have their own inherent restrictions. Now our goal is to bypass these restrictions and make it do something that we want the molecule to do, not that we watch what it does. Okay. So this is basically manipulating the photophysics of organic molecules through weak interactions and confinement. So basically we are going to put the molecule in a small place and watch what it does. Okay. Okay, you remember these things? So there are two things. If you put a molecule, this is our standard picture, S0, S1, T1, and then the fluorescence, radiationless, intersystem crossing, phosphorescence, and then radiationless. Okay. So fluorescence has a shorter lifetime, and then it is not supposed to quench. The phosphorescence are much harder to see, because the phosphorescence has a longer lifetime, and then it is easy to quench, because something lives for longer, then it can be quenched by oxygen. And then it is also the intersystem crossing, that is going from singlet to the triplet. In order to produce the triplet is very slow. So, because you have to have some spin orbital coupling that will enhance the intersystem crossing. Okay. Yesterday I mentioned something about heavy atom effect. You remember that? Remember it or no? Heavy atom effect. You remember? Tell me, what is heavy atom effect? You got the page right? You got it correct? You? What is that one? No, yesterday when I was talking about the singlet and the triplet, naphthalene, chloro-naphthalene, bromo-naphthalene, iodo-naphthalene, like that, right? And then I told you, in the case of iodo-naphthalene, you produce more triplets, or you see the absorption corresponding to forbidden transition S0 to T1 is much more in iodine compared to chloro-naphthalene. So, the iodine is a heavier atom. So, usually if you have a heavier atom, it will enhance the intersystem crossing. Did I tell yesterday or no? And then you also answered a question, if I remember correctly. We had a question about which one of them has more higher intersystem crossing, and then everybody said it is iodo-naphthalene. Okay, so I was sort of very happy that people understood. Now you seem to be sort of forgotten already. What is this heavy atom? I think you should remember heavy atom effect, right? You had the equation with the Z, that is the Ez to the power of 4. Z is atomic number. So, if you have a heavier atom close to the molecule, then that molecule will cross from singlet to the triplet, or from triplet back to the ground state faster than if there is no heavy atom close by. You got it? You got it. Okay. Now, that is a very important, very useful information to know. So, if you have a molecule, take it in some solvent, you will not see any emission. You take the same molecule in solvent like ethyl iodide. Ethyl iodide is CH3, CH2, I. Then you will see. Okay. So then you will see the phosphorescence from the compound. That is what we call as heavy atoms. Okay. Now, how do you bring this heavier atom closer to your compound? It is not that easy. So, you can put it in some solvent, but still it is going to be random. But if you have a supramolecular structure in which the heavier atoms are close by, then these and that will talk to each other, and this will get enhanced. Okay, so this is for example, you take here the phosphorescence, the rate constant is small, and the lifetime is long, and then long means bad news, because longer the lifetime, it can be easily quenched. There is no phosphorescence, and the emission quantum yield depends upon singlet, triplet crossing, that is also slow. All these things, everything is bad. So, if everything is bad, how do you make it good? Okay, that is the goal. Okay. So, here, so you have a singlet, and then singlet is undergoing intersystem crossing to the triplet, and then the triplet is going to emit light, that is going to be phosphorescence. So, your goal is to see lot of phosphorescence. That is what we want to know, because this molecule does not want to phosphorus. So now if you go from here, the singlet is sort of, there are other processes which is taking it away, either by quenching or chemical reactions, or it is the radiation-less process or faster compared to this. And also if you produce this, it is quenched by something else like oxygen. So there is something else in the solution, they come and quench it and there is nothing. So what you need to do to make this molecule emit strongly, somehow or other you have to keep it to go along this direction. At no stage it should go down. If it takes somewhere, it takes a different route, then that is not very good. Okay. So how do you make it to continue to go in the forward, but not taking a route in a different direction. Okay. So that is the things. So heavy atom effect is an atomic number effect that is related to the coupling of the electron spin and electron orbit motions. So it is a spin orbital coupling. So okay, we didn't talk in details all this stuff. It is a little bit more complicated. Most commonly, the heavy atom effect refers to the rate enhancement of a spin forbidden photophysical radiative radiationless transitions, and it depends upon the atomic number, that is the Z. Higher the atomic number, good. So if you have a periodic table like helium, neon, argon, xenon, things like that. So xenon will be much better than helium. If you bubble the helium into the solution versus the xenon into the solution, xenon ones will show the emission. Okay. Now the heavy atom may be either internal to a molecule or it could be external. So if you have, for example, naphthalene versus the iodo-naphthalene, the iodine is connected to the naphthalene, that is internal. That is basically you make the compound, you cannot remove the iodine, and now the iodine is stuck onto the naphthalene. Or what you can do is take the naphthalene and put this ethyl iodide. So they are not connected. So after the emission, you can remove the ethyl iodide. Okay, so that is one way to do this stuff. Okay, so here now, so you want to see what is the strategy to record phosphorescence at room temperature through supramolecular approach. Before we start this, phosphorescence is very hard to see at room temperature. Okay, that is why we are interested in. If it is easy to see, there is no point in spending time on this stuff. So phosphorescence you cannot see at room temperature. That is why we use a glass that is at 77 degrees Kelvin in using liquid nitrogen. So to see the phosphorescence, somehow or other you have to increase this rate constant, and then that is more, then you make more triplets, because if this rate constant is small compared to this rate constant, then this is not going to happen. Everything, the molecule will go through here. So first goal is somehow or other you produce more triplets. To produce more triplets, this number has to go up. This number to go up, this is singlet, that is triplet. They are different spins. The spin change depends upon the spin orbit coupling, which is directly related to the heavy atoms. Okay. So now that is first goal. You want to produce more triplet. That is okay. Second goal is after you produce the triplet, you want to have a strong emission. This rate constant should be large, and also you should stop this thing. This is the one which is going to be removing the triplet by quenching. That is, second molecule comes and interact with the excited state. So make triplets emit faster in competition with the quenching process. These two you have to achieve. If you have an idea how to achieve that, then you can see phosphorescence from molecules in room temperature. But normally it is not possible. Okay. So do you have any idea how to make it? You have an idea. You seem to be not. So you have an idea how to make it work. We want to find phosphorescence from naphthalene at room temperature. Naphthalene at room temperature does not phosphorus, okay, in solution. So, but you want to make it phosphorus at room temperature. So, okay, you have an idea. So the solution is here. You have to make more triplets. and you have to make this rate constant higher than the quenching rate constant. So all this you have to achieve the 2. If you achieve the 2, you will see phosphorescence. Okay, so the class has no idea what to do. Okay, now I will tell you what can be done. Okay, so what you do is you take, for example, you remember this cyclodextrins and things like that. Okay, cyclodextrin is the one of those bucket type of compound with a hole in the middle. Cyclodextrins is water soluble. Naphthalene is not water soluble. Is it naphthalene or what is the example here? Phenanthrene. They are very similar. Okay, so if you take phenanthrene in water, phenanthrene will not dissolve. Okay, and then if you take phenanthrene, but if you add a little bit of cyclodextrin into water, then the phenanthrene will dissolve. Phenanthrene, which is like a powder, white powder, put it in my water, it will float. If I add a little bit of cyclodextrin, put it inside, then if you shake a little bit, everything is gone. Okay, so the way it happens is this phenanthrene will go inside cyclodextrins. Inside the cyclodextrins is hydrophobic. So the inside part of it is not, it is more like an organic layer. So this molecule will go inside and phenanthrene will stay here. And then I also told you, if you take this the bromide or ethyl iodide, things like that, then you will see phosphorescence from the compound. But the only thing is you have to be very close. So the way to make it very close is you take the whole, put one compound, leave a little bit of space, then this compound will come inside and stay there, because that compound also does not like water. This compound does not like water, this compound does not like water. They both are looking for a place to go hide, and that place happens to be the cyclodextrins, that is in water. So when you put it in, you can see here these two are next to each other. So phenanthrene is sitting, and then there is this bromide sitting right next to it. So the bromine is a heavy atom. So when you excite it, this bromine will trigger this thing to go from singlet to the triplet. And once it goes to the triplet, it will again trigger it to go back to the singlet, which will be the ground state. So this one you can see here. So this is the phenanthrene fluorescence at room temperature in solution. There is no phosphorescence. And then this is the same solution. You have added little bit of this cyclodextrins. Now the fluorescence is small, phosphorescence is large. So it is pretty easy. Yeah. You have a question or?
We change the CH2Br2 to CH2Cl2, for example.
CH2 what?
Cl2.
Yeah.
The fluorescence will be enhancing or quenching?
Okay. If the heavy atom effect is directly proportional to the atomic number, tell me chlorine and the bromine, which one is heavier?
Of course, bromine.
Okay. So the bromine will do a better job than the chlorine. So if you take iodine, it will do even better job than the things. Okay. So this is an impressive picture, because you can see in a normal organic solvent, you see only fluorescence. In water, in presence of cyclodextrin, you see pretty strong phosphorescence at room temperature. You can bubble oxygen through the solution. Still it will not quench, because this one is sort of protected inside cyclodextrin. So oxygen cannot come there. Okay. So here, the question that you were asking. So for example, if you take the various atoms here, lithium, sodium, potassium, rubidium, cesium, thallium, and lead, right? And here is ionic radius. I don't think this is very useful. But tell me, which one has got a very strong spin orbital, which will induce a very strong spin orbital coupling? Which one? Last one. This one. Okay. So it depends upon the spin orbit coupling parameter. This number here, it is proportional to the Z, that is the atomic number. So you don't need to remember this number, but if you remember the atomic number, you can tell which one is going to be more. So, the lead has got very heavy compared to thallium. So, you can see this has got a higher number. So, if you have a series of salt, sodium chloride, rubidium chloride, put your compound and then crush it, then you will see the phosphorescence. So, you do not need to have the things, but some of these things are. So, suppose you dissolve this compound in water and then put your naphthalene or phenanthrene in water, you will see no effect, because naphthalene is not water soluble. These compounds are water soluble, but you will have to dissolve naphthalene in water for this to be able to work on the naphthalene. Okay, so here, so this is the, for example, go back to our pictures. This is crown ether, micelle, zeolite. Okay, crown ether, in the middle there is the place where you can draw the metal ions. Okay, but you can do this in, you don't need water for this. You can do this in organic solvents like hexane or benzene, like that. So, the greatness of the crown ether is it can draw metal salts into the organic solvents. Okay, this one is going to be doing this opposite. This is micelles, which can draw organic molecules into water. It is the opposite. And zeolites are solids. So, you can, if you put a naphthalene or a phenanthrene and then just crush this little bit, phenanthrene will go inside here. Okay. Now, okay, we got our organic phenanthrene in water, and we got our salt. Our phenanthrene is here, our phenanthrene is here. Now, how do you make it to phosphorus at room temperature? What do you have to do in order for this molecule to be able to phosphorus?